like the holy grail for the ancient knights. It seems like all physicists are talking about this. Let's understand what it means, why it's important, and how you go about attacking the problem.
It's important because it's finishing a revolution that Einstein started. We have general relativity, which is a theory of space and time, cosmology, gravity.
Structure of the universe as a whole, basically.
The structure of the universe as a whole, and space and time, what space and time are.
Right.
We have quantum theory, which is a theory of matter, radiation, atoms, elementary particles, and so forth. But they speak two different languages. They're based on different principles. They conceive of the world differently. And nature is one. Nature is a unity. So we want one fundamental theory. And that's the problem with quantum gravity, is to find that one fundamental theory.
Even though one is the description of the very small and one is the description of the very largest, still we need to combine them together?
Sure. If for no other reason, to have a sense of coherence, to have a sense of what nature is, to have something to tell our children what is the world, but also because there are experiments that probe a regime between them. And we want to be able to make predictions for those experiments and test our ideas and our theories.
And it's said that in certain conditions, like theoretically in the center of a black hole, or singularity, or at the beginning of the universe as a whole, everything was so crunched together that quantum mechanics actually had an effect on everything because everything was so small.
Yes.
So we have to figure this out.
Yes, and we are.
Okay. You sound very confident. So how has the field evolved?
So there are, roughly speaking, two kinds of approaches. There are approaches that ignore the fundamental lesson of general relativity, and there are approaches that embrace it. The fundamental lesson of general relativity is that space is not given a priori. There's no a priori geometry of space. Space is something dynamical, which evolves just like anything else evolves. You know, the building, the particles flying through the air.
There's no preferred frame of reference, so to speak. One thing, everything is oriented from one thing.
And no preferred geometry. The world is not Euclidean space as we were taught in high school. And these approaches, we call them background independent. In past times, they were called relational, because the geometry of space is a network of relations amongst the different things that happen, the different things that are. Now, the rest of physics and the rest of elementary particle physics ignores gravity and therefore takes a fixed space-time and then has things moving in it, and those are called background-dependent approaches.
And for the rest of physics, it's okay because you don't have to deal with some of the larger issues in what they're dealing with.
And you don't have to deal with this fundamental insight, which is that the structure of space, the geometry of space is not fixed, it's ever evolving, ever changing.
Because that factor doesn't affect when you're dealing like with basic atomic physics or whatever.
Absolutely.
Gravity is just too insignificant in that world.
Because of this mystery that it's so weak compared to the other forces.
Okay.
So string theory is the only real viable, or still possibly viable approach, which is background dependent. But certainly, if it succeeds, that's a big if, it will have to come to the other side and be background independent. So for me, the interest, and for many of us who work on it, we start with this requirement that we have to embrace the basic discovery of general relativity, of Einstein and general relativity. And indeed, there's been a lot of success. So one of the things that's often said, which is false, is that you can't combine general relativity and quantum mechanics. Well, you can. It was discovered how to do that by a program of research called Loop Quantum Gravity. Started with a Bayashtakar and then several of us contributing, Ted Jacobson, Carlo Rovelli, myself. And we did find that one could consistently combine, just as given, the principles and the equations of general relativity and quantum mechanics. So there is such a thing. I don't know if it is the true theory of nature, but it is a completely well-defined theory, and many people study it.
What are the problems that it's faced?
So the big problem is the following. Just like when you quantize an atom, you discover that there are discrete energy levels. When you quantize geometry, you discover that there are discrete pieces of space that fit together to make all the possible geometries of space. And we discovered in Loop Quantum Gravity a precise description of these discrete pieces, and they fit together into networks, which we call spin networks. And so we have a precise picture at the Planck scale, this tiny, tiny scale, of the quantum geometry of space by combining these pieces. Okay. The question is, why is it that when you aggregate vast numbers of these tiny pieces of space, you get something that looks like three-dimensional geometry? That's the problem of the emergence of space. And that's a problem that any fundamental approach to quantum gravity must face. And it's the problem on which we begin, I think, over the last 5-6 years to have a real handle on it. And there have been some results that show us space emerging from this more discrete quantum geometry.
So what you're saying is that space is not the most fundamental thing that we have, which in common perception seems to be. It seems like space is space and we move in it in 3 dimensions. But you're saying that space is an emergent property, like water is the emergence of hydrogen and oxygen in some unusual way, that space emerges from something else.
Precisely. And just like in the science of materials, it's a key question if you put together a lot of atoms, a lot of water molecules, for example, under some conditions you'll get a gas, under some conditions a solid, and ice with very interesting properties, under some conditions a liquid. Can you derive that from the properties of the material, plus the fact that there are a large number of them? And we begin to be able to, there begin to be some results that show, for example, that when you combine them, that the gravitational force is recovered, that gravitational waves propagate correctly. And one of the things that's surprising and fascinating is that just like water molecules can combine under different conditions in different phases, there can be different phases fundamentally. So one phase is space, the way that we see it, but there could be other phases where there's nothing like space. There's still the fundamental physics going on. And one of the more interesting directions is that people start to conceptualize, Fortini Marcopoulou, Thomas Kanoka, and some other people, that what was going on in the very early universe might have been a phase transition from this other phase with no space to a phase with space, and we call this geometrogenesis, the genesis of geometry.
Now, I notice you haven't mentioned